Hello, everyone, and welcome. I'm Dr. Sayantika Chowdhury, and today we're going to dive into something that's really at the heart of all digital electronics, logic families. Now, I know what you're thinking, but trust me, this is more than just circuits. It's actually a story of powerful clans, a kind of great family feud, all fighting to be the best in the digital kingdom. So let's get right into it.
Okay, so to get started, I want you to picture an integrated circuit, an IC, as this massive, bustling city, all crammed onto one tiny little chip. Now, for any city to work properly, all the different neighborhoods have to be able to talk to each other, right? Well, these neighborhoods, these are our logic families. And just like real families, each one has its own personality, its own strengths, and of course, its own weaknesses.
So, before we get into all the drama, let's properly introduce the main characters in our story. What exactly is a logic family?
Well, think of it like this. A logic family is just a group of logic gates all built using the same basic technology. So in our city analogy, these are like the different districts. Everyone living in one district, they all follow the same rules, they speak the same language. That's what we mean when we say compatible logic levels. They're all plugged into the same power grid, and together they become the essential building blocks for our entire digital world.
Now, in any big competition, you've got to have rules, right? And in our family feud, we judge these different families based on some really key engineering parameters. So let's have a look at how we're going to keep score. First up, we have something called propagation delay. This is actually very simple. It's just how fast a gate can react. Think of it as the family's reaction time. In our digital city, it's like the commute time. A low propagation delay is like a high-speed metro. It gets you from the input to the output super fast. A high delay? Well, that's like being stuck in traffic. So for speed, shorter is always better.
So just to recap that, the one parameter that tells us everything about how fast a gate can react to a change is the propagation delay. Got it? Good.
Next up is noise margin. Okay, imagine you're trying to have a really important conversation in a very, very noisy room. Some people can just tune out the noise and understand you perfectly, right? But others get easily distracted. Well, noise margin is basically a logic family's patience with all that electrical noise. A family with a high noise margin is great because it can understand the signals clearly, even with a lot of disturbance going on. All right, next we have fan in and fan out. Let's say a gate is like a team leader. Fan in tells you how many people can report to that leader at the same time. And fan out, well, that's how many other gates that one leader can give instructions to. So a high fan out is a really good quality. It means one leader can command a really large team, which makes our circuit design so much simpler.
Now here's the most crucial point. There is always a trade-off, a classic fight between speed and power. We measure this with something called the figure of merit. It's just the propagation delay multiplied by the power consumption. Our goal is to always get a low figure of merit. And a good way to remember this is that the best families are both powerful yet deliberate, that is, PD or power delay product. This trade-off is really the central conflict in our whole family feud.
Okay, so now that we know the rules of the game, let's meet the two major clans. First, you've got the bipolar families. They build their gates using bipolar junction transistors, or BJTs. And on the other side, we have the unipolar families, who use MOSFETs. These are the two great houses that have been battling for control for decades. So let's start with the bipolar clan. You can think of them as the old guard, the pioneers who really laid the foundation for all modern computing. We'll look at two of its most famous members, TTL and ECL. First, let's meet TTL, which stands for transistor-transistor logic. If TTL was a car, it would be that reliable family sedan. It's not the fastest, not the fanciest, but it's sturdy, it's dependable, and for a long time, it was absolutely everywhere. For decades, TTL was really the backbone of the digital world. And this really shows you just how important it was. On the left, you see a basic TTL NAND gate. Simple enough. But on the right, that's its legacy. All the early computers, the machines in our factories, the test equipment in labs, so much of it ran on this incredibly reliable workhorse technology. But TTL also had a very clever trick up its sleeve, tri-state logic. So besides the usual high state and low state, it could go into a third state called high impedance. The best analogy is a conference call. You can be speaking, which is like a high state. You can be listening, a low state, or you can put yourself on mute and be completely disconnected from the conversation.
This was so useful for connecting multiple devices to a single common line, which we call a bus.
So what was it again that made TTL the go-to choice for so long? Well, it was its reputation as a reliable, robust, and widely available technology. It just worked. Now let's meet TTL's cousin, ECL, or emitter-coupled logic. So if TTL was the dependable family car, ECL is a Formula One race car. It is blindingly fast. In fact, it's the fastest of all the logic families. But just like a race car, it is incredibly power-hungry. It's not at all practical for everyday use.
And here you see that trade-off again, laid out so clearly. The big pro, unmatched speed. We're talking propagation delays as low as 1 nanosecond. But the cons? My goodness, it consumes a massive amount of power, and its noise margin is pretty poor. It was built for one thing, and one thing only, pure speed.
So if you're in a situation where you need pure, unadulterated speed and nothing else matters, which family are you going to choose? The Sprinter, of course, ECL. The bipolar families, they really had their time in the sun. But a new champion was rising up from the unipolar clan, a family that would completely take over the modern era. So let's meet the CMOS family. CMOS, it stands for Complementary Metal Oxide Semiconductor. Now, it's not the absolute fastest, but it is the ultimate all-rounder. And its superpower, the one thing that allowed it to win this great family feud, is its unbelievable power efficiency. It just sips power instead of gulping it down like the others. Just look at these advantages. High noise immunity, excellent. The ability to pack a huge number of gates onto a single chip, fantastic. But the real game changer is right here, low static power consumption. What this means is that when a CMOS gate isn't actively switching, it uses almost zero power. This single fact is what made our modern world of portable devices, like smartphones and laptops, even possible. So, thinking back, why did CMOS become the undisputed king for everything from our phones to our laptops? It was that revolutionary low power consumption, which is absolutely essential for our battery-powered world. Okay, so we've met all the main contenders in our family feud. Now let's put them all side by side and give out a final report card to see how they all stack up. This table really tells the whole story, doesn't it? You've got ECL, the speed king, but at a huge power cost. Then you have TTL, a solid balance, but still pretty thirsty for power. And finally, CMOS. It's about as fast as standard TTL, has excellent noise immunity, but look at that power consumption. It's incredibly low. And that is exactly why it became the champion for pretty much every modern application you can think of. So, you see, while this particular family feud might have a clear winner for now, that central conflict, the battle between speed and efficiency, is far from over. And this brings up a really crucial question for us as the next generation of engineers. What will the technology of tomorrow demand from us? You know, this fundamental trade-off that we've explored today? It's still this single most important challenge that engineers face. It doesn't matter if you're designing faster CPUs or longer-lasting batteries for electric cars or the next generation of AI. Understanding this constant battle between performance and efficiency isn't just about passing your exam. It's about learning the core language you will use to design the future. And that's why what you're learning right now truly matters. Thank you.